Welcome to Chapter 8 of MEC260, our course on engineering statics. This time we're going to study friction. Your assignment is to read Chapter 8 in our book Vector Mechanics for Engineers, and then on the Connect website you will have homework number 11. We're going to study first frictional forces. The image on the left shows a frictionless slide. You've probably seen this image many times because it's a standard part of freshman physics. In this slide, the block slides down the incline with a downhill force of mg sine theta, where theta is the angle between the ramp and the horizontal. The force of gravity is equal to mg. There's a normal force pushing back on the block from the slide equal to mg cosine theta. And in freshman physics, there is no friction, so the block slides smoothly down the ramp, and the acceleration of the block is going to be g sine theta. When we study friction, we model the sliding friction by multiplying the normal force by a coefficient of sliding friction mu. The sliding friction acts against the downhill force to effectively slow the box down. We have two types of friction. One's called dry friction, the other's called wet friction. We can understand a dry friction from this photo of an autonomous vehicle driving on a dry road on a nice sunny day. The dry friction force acts against the tires on the road, and that's what allows the tires to maintain a continuous contact with the road at high speeds. The car is nice and stable, and all these autonomous algorithms, even with that guy in the car driving the car as backup, are going to do pretty well because the force of friction is very predictable and stable. Now imagine an autonomous vehicle in the picture on the right side. This vehicle is driving on a wet road in the pouring rain. The tires channel some of the water away, but hydroplaning can occur, which can cause the driver to lose control of the vehicle. Not sure if you want to be in an autonomously driven vehicle in a pouring rainstorm, especially if you're going on a steep downhill, because the algorithm's going to get all confused. The hydroplaning creates a very unpredictable force of friction, and you really would rather have the driver in there to control the vehicle. On the bottom of the slide, you see a quart of STP engine oil, which is used to create wet friction between the pistons and the cylinders of an auto engine. Without using wet friction and a nice low friction force between the piston and the cylinder, you'd waste a lot of the energy of the engine dissipated in friction. And if you had dry friction in an engine, you would destroy the piston very quickly, which is what happens if you run out of engine oil. The moral of the story is, if you ever get the oil low indicator on your auto engine, stop immediately and either get some more oil in there or have the car towed. Dry friction and auto engines do not mix. $4,000 later, maybe you'll get your car back. The slide will illustrate the laws of dry friction. In figure 8.1a at the bottom, we have a block of weight W acting on a horizontal surface, with a normal force N acting upwards towards point A. In 8.1b, we apply horizontal force P to push the block to the right. In this case, the block does not move because we've got static friction force F pushing back. On the other hand, if you made P enormous, you would definitely move the block. Force F, the friction force, is caused by the irregularities of the contact area between the block and surface. And to illustrate that, we show you here in the lower right a microscopic view of surface irregularity. Now, the actual height of these roughness of something that we use in everyday life is very, very small. It can vary from a couple of thousandths of an inch for something we call rough to a few angstroms for something we'd call incredibly smooth. Nevertheless, when you have this type of rough profile on one part, say the block, and you have the mating surface upside down with its roughness on the surface, you can see quickly that those profiles are not going to mate perfectly, and there's going to be all kinds of high spots and low spots that mate with each other. And that's what we mean by irregularities of contact area, causing two surfaces to tend to stick to each other. Figure 8.1c in the lower right shows that if you increase that force P, the friction force F also increases. And F opposes P until the magnitude of F reaches what we call F sub n, its maximum value. If P is increased further, the friction force cannot stop the block, and it starts sliding. And F drops from F sub m, here in the graph, to a lower value, F sub k, which we call the kinetic friction force. And the block keeps sliding with increasing velocity while F sub k remains about constant. Which is why I said before, if you make P large enough, you can make this block go flying, and if there's an edge of this table somewhere, it's going to go flying off the edge until it lands on the floor. As F increases from 0 to F sub m, so that's this part of the curve, point A, which is the point of application of our normal force A, moves to the right. And the couples formed by P and F, so P and F are equal and opposite, but separated by a certain distance, that would create a moment which would go clockwise, get balanced by the couple formed by W and N, where W and N are equal and opposite and separated by a certain distance, and they create a moment that goes counterclockwise. And if point A reaches point B before force F reaches its maximum, the block will start to tip about point B before it starts to slide. So this whole block would actually start to rotate around point B rather than slide along. For static friction, the maximum frictional force equals mu sub s times n, the normal force, where mu sub s is the coefficient of static friction. And for kinetic friction, F sub k is equal to mu sub k times n, where mu sub k is the coefficient of kinetic friction. Coefficients mu sub s and u sub k do not depend upon the area of the surfaces in contact. Rather, both coefficients depend on the nature of the surfaces in contact, and experimentally obtained values tend to have no better than 5% accuracy. Approximate values for mu sub s for various combinations of dry surfaces are listed here in Table 8.1. These values are dimensionless, and that's because F sub m has units of force and n has units of force, so mu sub s by definition can't have any units, or you can't make that equation. Corresponding values of mu sub k are about 25% smaller, which is why the kinetic friction force is going to be less than the static friction force. And these ranges are very wide. You have to consult a lot of different references with a lot of detail on the types of metal and types of leather and types of wood until you can even get within a 5% accuracy reading of what these coefficients are. So take it with a grain of salt. 4 situations occur with a rigid body on a horizontal surface. In figure 8.2a in the lower left corner, forces are applied to the body act normal to the surface, and there's no frictional force. The normal force is just equal to the load P plus the weight W. In 8.2b, here in the lower right corner, the applied forces have a component parallel to the surface of contact, which we would call the horizontal force P sub x, but they're not large enough to set the block in motion. We can find F via the equations of equilibrium for the block, and here is F, the frictional force acting to resist motion. And because force F is less than the max F sub m, the equation F sub n equals mu sub s times n cannot be used to determine F. In figure 8.2c in the lower left corner, the block is about to slide. We call this motion is impending. And the force F is equal to F sub m, the max value. In this case, F and N balance the applied forces. And both the equations of equilibrium and the equation F sub m equals mu sub s times n can be used. Here in the lower right, in figure 8.2d, the body slides due to the applied forces, and equilibrium no longer applies. However, the force F does equal to F sub k, and we can use the equation F sub k equals mu k slash n to solve for the force. Let's discuss angles of friction. In figure 8.3b in the lower left, force P has horizontal component P sub x, and force R has horizontal component F. R then forms an angle phi with N, which is vertical, and that's the normal force to the surface. In figure 8.3c, you increase P sub x until motion is impending. An angle phi gets bigger, and it keeps going up until it reaches phi sub s, which we call the angle of static friction. In figure 8.3c, in the lower right corner, the angle of static friction phi sub s follows these equations. The tangent of phi sub s, which is just opposite over adjacent, is equal to F sub m, where F sub m equals P sub x, divided by n, the normal force. But because F sub n equals mu sub s times n, we have a simpler equation that tan phi sub s is equal to mu sub s. And in figure 8.3d, here in the lower left corner, the block moves. F drops to F sub k, and phi drops to a lower value, phi sub k, which is the angle of kinetic friction. And phi sub k follows this equation. Tangent of phi sub k, this angle, is equal to opposite over adjacent, which is equal to fk divided by n. But because fk equals mu sub k times n, we get the simpler equation that tan of phi sub k is equal to mu sub k. In figure 8.4, a block rests on a board subject only to its own weight W and the reaction R. And in 8.4a, the board is horizontal, and the force R is perpendicular to the board and balances the weight W. But in 8.4b, we put the board at an angle theta with the horizontal. So here's theta, there's theta 2 to the horizontal. And R is not perpendicular to the board, but continues to balance W. So here's force R, which has a normal component, N equals W cosine theta, and that's normal to the surface of the slide and the block. And it has a tangential component, which is parallel to that same surface. We call that force F, which is equal to W times sine theta. And in figure 8.4c, theta increases and the motion becomes impending. An angle theta reaches its max value, which we call the angle of repose. And in figure 8.4d, we further increase theta and the block slides down. And theta drops to its lower value, phi sub k. R is no longer vertical. We see here, there's R, it's not vertical anymore. And the forces on the block are unbalanced, which of course is why the block is moving. That's the definition of no longer being in equilibrium when parts start to move. In figure 8.6a, the block and board are in contact with frictional forces equal and opposite per Newton's third law. And in figure 8.6c, the free body diagram is drawn with the direction of the frictional force, so here's our frictional force, opposite to the direction of, or sense as we call it, of impending motion. And that's the definition of how you draw the frictional force, is you imagine in your mind, hey, which way is this block going to move when the angle of the slide with respect to the Horizontal gets big enough, figure that out, and then the opposite direction to the impending motion. There are three methods of solving problems of dry friction. We'll take them one at a time with a couple of examples. In method 1, the known quantities are the applied forces P and W and the coefficients of friction. And the unknown quantities are the normal force N, the friction force F, here's F, required to maintain equilibrium, and F does not necessarily equal mu sub s times n unless F is at its maximum. And the other unknown is, does the body remain at rest or will it move? In order to solve these problems, you draw the free body diagram shown in Figure 8.6 below, and you solve the equations of equilibrium, and you compare the magnitude of the friction force F with its maximum value, F sub n, which is equal to mu sub s times n. And if the force is less than the maximum value, the body will remain at rest. But if the force is greater than the maximum value, then the body will move, and then the new frictional force is mu sub k times n. Here's sample problem 8.1 to illustrate the method. A 100-pound force acts on a 300-pound crate placed on an inclined plane. The coefficients of friction between the crate and the plane are mu sub s equals 0.25 and mu sub k equals 0.2. And we're going to determine whether the crate is in equilibrium, and then we'll find the value of the friction force. We'll assume that F is directed down and to the left, and we'll draw the free body diagram of the crate and solve the equilibrium equations. Now, we've already taught you that generally you want to assume that friction is opposing the impending motion, but we don't know if the impending motion is going to happen at all. And another side point is that even though we've drawn F going down and to the left, if our assumption is wrong and motion really is impending after all, we're just going to get a negative number for F, and the direction of F is just going to be up and to the right. So the problem will fix itself easily enough. In step 1, we draw the free body diagram with the assumed direction of F, and as noted, this is somewhat counterintuitive, and if we get it wrong, then F will be going up and to the right. Here's our 300-pound weight, which does go vertical with gravity. Note that we've rotated the axes to have X go down the center line of the crate and Y is normal, as it should be, to X. And this 3, 4, 5 triangle has been reoriented, in this case lining up the long side with the 300-pound force, but it's still consistent once we rotated the axes with this 3, 4, 5 triangle. Here's our normal force, which acts normal to the x-axis, where the x-axis is drawn on the inclined plane. And in step 2, we will solve for the required values of F and N to maintain equilibrium, which means that in equilibrium, the objects are assumed to be not moving. We sum the x forces along this axis. We've got our 100-pound force going in the positive x direction. We subtract 3/5 of the 300-pound force, which is the component of this 300-pound force along this x-axis. That's in the negative direction. We subtract F, and F is going in the negative x direction. And we find, as I predicted, that F is just minus 80 pounds, which means that F is going opposite the direction of the impending motion. The impending motion is down and to the left because that's where gravity and also our common sense would tell us that the crate's going to move. In step 3, we find the friction force that may be developed between the crate and our plane, and here's our plane, by using the coefficient of static friction. And we find that the maximum friction force that can be developed is mu sub s times the normal force, where we had calculated the normal force in the prior slide as equal to 4/5, meaning in the y direction, 4/5 of 300 pounds. And now in order to find the maximum frictional force, we multiply that 240-pound force by 0.25, and we see we only get 60 pounds. But that 60 pounds force is less than the force required to maintain equilibrium, which was the 80-pound force, which means that the crate's going to slide down the plane. Step 4, we find the actual value of the friction force by using our coefficient of kinetic friction. We take mu sub k of 0.2 and multiply by 240 pounds to get 48 pounds. We put all the forces in to try to understand what is the force that will actually accelerate the crate down the incline. We've got a 100-pound force acting up. We've got 3/5 of this 300-pound force, which is going to make the crate move down the ramp. It's opposed by a 100-pound force, maybe someone pushing on the crate, acting up. And it's also opposed by a 48-pound force of friction. And when we subtract the 100 and the 48-pound force from 3/5 of 300, we find that the net force that's going to push the crate down the incline is 32 pounds. Our second method of solving problems of dry friction, our known quantities are applied forces P and Q, and the fact that we know that motion is impending. And in this problem, the unknown quantity is just mu sub s, coefficient of static friction. We draw our free body diagram, and we solve the equations of motion to find F and N. But now, because motion is impending, we know that F equals F sub m, and we can find mu sub s by using the equation mu s equals N divided by F sub m. We know in method 3 that the coefficients of friction are defined at mu s and mu k, and we're given the fact that motion is impending in a known direction. Now the unknown quantities are the applied forces P and Q. And in order to solve this problem, we've got to draw the friction force opposite to the direction of the impending motion. And we've got to solve the equations of equilibrium with F sub m, meaning the max frictional force, equal to mu sub s n. And we're going to be using various friction angles to simplify the problem. We're also going to be using force triangles. We love force triangles. We're bringing them back from Chapter 2 and 3 one more time. Here's a sample problem 8.2 to illustrate the method. In this problem, a support block is acted upon by two forces. And the coefficients of friction between the block and the incline are mu sub s equals 0.35 and mu sub k equals 0.25. And we'll determine the force P, which is required to start the block moving up the incline, keep it moving up, and prevent the block from sliding back down. We have the free body diagram shown in the lower right. We're going to include our 800 Newton force acting down, which is the weight, if you will, of the block. So a big heavy steel block. We've got our horizontal force P, and we've got this force R exerted on the block by our incline. In order to solve the problem of what is the force to start moving the block up the incline, we add in this force triangle the friction force to the original 25-degree angle of the incline. Now P is perpendicular to our 800 Newton force down for the weight, and that means our force triangle is going to be a right triangle. So here's P, and there's the 800 Newton force. Those are the first two arrows you would draw in. And then you would draw R as connecting the tip of the 800 Newton arrow to the tail of the P arrow. And this angle between R and the 800 newtons is this angle between R and the vertical. And that's the critical step that you have to make for a force P defined as what do you need to start moving up the incline. You add the 25-degree angle for the incline plus your friction angle, 19.29 degrees, and you calculate the friction angle as tangent of the friction angle is just equal to mu sub s, the coefficient of static friction, which is 0.35, and the arctangent of 0.35 is 19.29 degrees. Therefore, the angle that we put in here is 44.29 degrees. Then, because this is a right triangle, P is equal to the 800 Newton force times the tangent of the 44.9 degree angle. P is 780 newtons. Now we'll determine the force P required to keep the block moving up the incline. In this case, you add the 25-degree angle for the incline to the friction angle, but now you're using the friction angle phi sub k, not phi sub s. And mu sub k is only 0.25, not 0.35. Its arctangent is only 14.04 degrees. This angle here comes out to 39.04 degrees. And 800 newtons times the tangent of 39.04 degrees is only 649 newtons. You got to push at 780 newtons to get the block started. But once you get the block started, you only have to keep pushing at 649 newtons. So the load gets lighter. And that's because the coefficient of kinetic friction, sometimes also called sliding friction, is less than the coefficient of static friction. Now we'll determine the force P required to prevent the block from sliding back down. Motion is now impending downward. So you calculate the friction angle as 19.29 degrees, but now you're subtracting it from 25 degrees. So the net angle of R with respect to the 800 Newton force is only 5.71 degrees. P, the force required to keep it from moving back down, is only 80 newtons, far less than the other forces. The frictional force of static friction is acting to prevent the block from sliding down the incline. So you, as the one applying force P, you don't have to push so hard anymore because now friction's helping you. Wedges are simple machines used to raise heavy loads. They apply a low force at a fairly shallow angle, where the angle is defined in this wedge as the angle between this top face and the horizontal, giving them a significant leverage on very heavy loads. And due to high friction between this surface of the wedge and the load surface, the wedge remains in place under the load. This wedge is model HK-16T, and it lifts objects vertically where an access gap of only 3/8 of an inch is available, and it has a 16-ton lifting force. And if you want to get more than 16 tons, you just use more wedges. Here is how the wedge relates to the load. Here's your horizontal surface. There's the angled surface of the wedge, and you push it underneath a narrow gap in what you're trying to pick up. In this case, it was a big steel beam. In this case, it was a large machine structure where 2 wedges were used, and there was only a tiny little air gap under here. So you put this wedge under that point, put that wedge under the point, apply hydraulic pressure to this line and that line, and you will see this whole machine starts to lift up. The reason you need to lift up machines with wedges is very often you want to move them. But in order to get the machine off the ground high enough so that you can get production moving equipment underneath the machine to move it around the factory, you got to get it off the floor at least a couple of inches. If you watch the video that is showing these 2 hydraulic wedges lift up this big machine, you'll get to see it in action. In figure 8.7a, block A rests against vertical wall B. So here's block A, vertical wall B, and we can raise block A slightly by forcing wedge C between block A and a second wedge D. And now we want to find the minimum value of the force P pushing across on this wedge to move the block. We know the weight W of the block, and that weight W would act just straight down in the picture. And figure 8.7 B and C show the free body diagrams of block A and wedge C. The weight W of this block, of course, needs to be known. The more the block weighs, the more you're going to have to push with force P to get block A to go up. The forces on block A include its weight going down and the normal and friction forces at the surface of contact with wall B and C. When we first start pushing on the wedge, force F1, which is the downward friction force of the wall on block A, is equal to mu sub s times N1, where N1 is the normal force pushing off the wall to the left on the block. And F2 down here is equal to mu sub s times N2, where N2 is the force pushing up on the block from the wedge. And then we also have a force F3 equal to mu3 N3, where that force F3 is the frictional force between this bottom angled surface of wedge C and the top angled surface of wedge D, and that angle is 6 degrees. Friction forces must be shown with the correct direction. And because the block moves up, force F1 exerted by the wall on the block acts down. And because the wedge C moves to the right, the motion of a block A relative to C would be to the left. Then the normal force N2 exerted on block A by wedge C acts up, equal and opposite force minus N2 on wedge C acts downward. Here's minus N2 acting downward on the wedge. Here's minus F2 acting across this top of the wedge. And then here's N3 and F3, which is the normal and frictional forces between wedge C and wedge D. Friction force F2 exerted on block A by wedge C acts to the right, and equal and opposite force minus F2 acts on wedge C to the left. Friction force F3, which is here, exerted on wedge C by wedge D also acts to the left. And the weight of the wedge is very small compared with all of the other forces involved, and it's routinely neglected from this type of analysis. We can reduce the number of unknowns to 4 by using the generic equation F equals mu sub n, and we apply that generic equation to F1, F2, and F3, leaving us with the 4 unknown variables N1, N2, and 3, and force P, which is what we're solving for. Because block A and wedge C are in equilibrium, we can obtain 4 equations used to find P, and we'll need them because we got P, N1, N2, and N3. Each free body that we will draw is subject to 3 unknown forces, and we're going to use our favorite, the force triangle, to find those unknown forces. Let's take a look at a sample problem of how to do this. In sample problem 8.5, we calculate the horizontal wedge force P, which in this case is going to the left, applied to wedge A to move block B either up or down. We know that mu sub s equals 0.35 between all contact surfaces, and we'll determine force P, first to raise the block, then to lower it. We know that normal and friction forces act between the wedge and the block. And to raise the block, you have normal and friction forces on the left wall, and to lower it, those normal and friction forces are on the right wall. We have 3 unique forces act each on block B and wedge A, and we're going to use our force triangles. Step 1, we draw the free body diagrams of block B and wedge A when raising the block. We're also going to draw the force triangles. Here we see the free body diagram for raising the block. We'll be able to use the law of sines to find the desired forces. Because mu sub s equals 0.35, the angle of friction is taken from the inverse tangent of 0.35, which is 19.3 degrees. R2, which is the resultant for the left wall, is drawn at an angle of 19.3 degrees relative to the horizontal, because that's the friction angle. R1, which is the resultant of the wedge on the block, is drawn for raising the block at 19.3 degrees plus the 8-degree angle of the wedge, or 27.3 degrees. And then, of course, we have our 400-pound force acting down on the block, which is the weight of the block. When raising the block, the friction force F1 on block B due to wedge A acts to the left. Therefore, we draw R1 pointed at least partially to the left, and partially to the left, that is, by 27.3 degrees. Now we've got the right angles and relative directions for R1, R2, and the 400-pound force. We can draw them tip to tail in the force triangle. Here's the 400-pound force acting down. The 400-pound force relative to R2 is at 90 plus 19.3 degrees, because R2 has to be moved. That 19.3 degrees relative to the horizontal adds to the 90 degrees to create a 109.3 degree angle. We have our 27.3 degree angle for R1 relative to the vertical, and that's what this 27.3 degrees is. And then the third angle is just 180 minus 27.3 minus 109.3, that's 43.4 degrees. Law of sines says we take the ratio of R1 to the sine of the angle opposite of it, which is 109.3 degrees, is equal to the 400-pound force divided by the sine of its opposite angle, which is the sine of 43.4 degrees. Solve that equation, and R1 equals 549 pounds. Now we can draw the force triangle on the wedge for lifting the block. Resultant R1 is at an angle to the vertical equal to 8 degrees for the slope plus phi sub s. There's your 27.3 degrees. R3 is the resultant of the ground on wedge A, which is drawn at a 19.3 degree angle to account just for the friction angle. And both R1 and R3 act to the right. Now we can draw our force triangle. There's R1 acting down relative to the vertical with 27.3 degrees. It's angled with respect to R3 is 27 degrees plus 19.3 degrees. That's how we got 46.6 degrees. And then this third angle becomes 70.7 degrees between P and R3. Force P is to sine 46.6 degrees, as the 549-pound force is to sine of 70.7 degrees, at which point P is 423 pounds, acting to the left. Now we'll draw the free body diagrams of block B and wedge A when lowering the block. The friction force is on the right side of block B. Resultant R2 is at an angle to the horizontal equal minus phi sub s. Resultant R1 is at angle to the vertical equal 8 degrees of slope minus phi sub s, and we use the law of sines to find R1. Here's our 400-pound force acting down. There's our 11.3 degree angle between R1 and the vertical. Here, between R2 and the 400-pound force, we have an angle of 90 minus 19.3 degrees, which is equal to 70.7 degrees. And then the third angle just comes from taking 180 degrees and subtracting the 70.7 and the 11.3 degrees to get 98 degrees, We again use our law of sines and find that R1 equals 381 pounds. In step 5, we draw the force triangle on the wedge for lowering the block. Result in R1 is at angle to the vertical equal to 8 degrees, slope minus phi sub s. That's why we get a minus 11.3 degree angle here. And the friction forces R1 and R3 on wedge A act to the left. Using our law of sines, we can find P. First, we show you how we drew the force triangle. P is the easy one. That acts to the right. R1 equals 381 pounds. That force is drawn next, and then R3 acts up. R3 relative to the vertical is at our 19.3 degrees. So here's our 19.3 degrees. And this angle between P and R3 then becomes 90 minus 19.3 degrees, which is 70.7 degrees. And then this angle between R1, which is 381 pounds, and R3 is you add the 19.3 degrees and the 11.3 degrees to get the relative angle between those two forces. That's 30.6 degrees. We use our law of sines here in the lower right, and we find that P is equal to 206 pounds, which is less than half the force of 423 pounds that it took to raise the block. Square thread screws are frequently part of jacks, presses, and other mechanisms. And the analysis for a block moving along square threads resembles that of a block sliding along an inclined plane. And we're going to use similar mathematics to do that. On the left, you see what's called a short-lift bottle type screw. You rotate this handle, which turns the screw, and then up top here, whatever object is sitting on there moves up. Here you have what's called a scissor jack for replacing a flat tire on a car. I've had the lovely pleasure of doing that very often. And in the middle is the square threaded rod, and you turn a crank that turns this small eye loop, and the screw rotates, and the jack goes from mostly closed to mostly opened. This part here is underneath the car, and then the car goes up and you can take out the spare tire. And if you want to watch a couple of good videos on this subject, these two URLs in this slide both explain how the actual process works, where the scissor jack takes the weight off the car one tire at a time. And if you only have one tire, you only get to do this once. If you got two flat tires, you get to do it twice. Now in my case, the last time I remember doing this was trying to get to Newark Airport to catch an early morning flight, having the fruit truck in front of me spill a large carton of fruit, driving along right in front of my car. I went over this wooden box, in which case my left front tire went flat pretty much immediately. I then limped off the bridge at 10 miles an hour, where all the morning commuters were honking their horns and screaming at me. On the shoulder, at the end of the GW Bridge on the Jersey side, I had the pleasure of fixing a flat tire and then still trying to make my flight, while I was filthy from all the dust on the side of the road. Needless to say, it was a very unpleasant experience, and if I never do it again, that's fine by me. But I thought I would explain this to you, so now you all know how to use a scissor jack. Here's a type of threads that are in these scissor jacks and in these jack screws. Normally it is a square thread, which is what we're going to analyze, and it gets its name from the fact not that the view of the threads itself is square, but if you make a cross section which goes right down the central axis of the screw, in the cross-sectional view the thread has the look of a square opening and then square metal, square opening, square metal. What is more commonly used for threaded screws and bigger old machine screws is what's called an Acme thread, where the side walls of these screws are on an angle, typically 29 degrees. Much less friction in those mechanisms and much easier to machine. But on the other hand, the analysis is very tough, and in this class we're only going to do some force analysis on the square threads. In figure 8.8, the jack, as we're showing you here with the handle, and the handle rotates, you put a force P on the handle, it rotates, and that allows the thread to move up inside this base, and whatever weighs a whole lot, which is weight W, is on top of this surface here that I'm showing you. The jack carries that load W, and the threads are supported here at the base. And the contact between the screw and the base takes place only along these threads that I'm showing you. So reduces, of course, the amount of friction that you have in the system. And as you rotate the handle with force P, you then get to raise the load, and you have to put a lot of force in to do that. And in order to lower the load, you rotate the handle in the opposite direction, still with a modest amount of force to overcome the friction in the threads. But at that point, gravity is your friend, and usually you have to apply a force that's less than half of what you needed to do to lift the load up. In figure 8.9a on the bottom, we unwrap the threaded hole of the base and we model it as a block going up an incline. The lead L of the screw is the linear distance through which the screw thread advances in one turn, and in this figure 8.a picture that means up and down. And the mean radius, small r, is the average radius of the circular screw thread. Let me show you that. If you're inside the screw thread, it won't be this outside radius, and it won't be this inside radius. It would be half the distance between the two, which is roughly where I'm drawing my mouse. The analogous angle theta of the incline, here's theta, is equal to the arctangent of L over 2 pi r. And that angle theta is called the lead angle. The free body diagram of the block includes the load W and the reaction R, which is the base of the thread, so there's R, and includes our horizontal force Q, which has the same effect as this force P, which we were exerting on the handle. And Q should have the same moment as P about the axis of the screw, which means Q equals P times small a divided by R, where a is this distance from the edge of the handle to the location of where the force is applied. And essentially a represents the length of the handle. We find Q and thus P required to raise load W from the free body diagram of 8.9a. We let the friction angle equal phi sub s because the load is usually raised through a series of strokes, which is what it was like for me on the George Washington Bridge, where I sure didn't turn that handle 100 times to get my car raised up enough to get the spare tire out. It was hard work. So I'd do a quarter turn, stop, another quarter turn, stop. Most of the time I was exhausted and I was overcoming static friction. Now if I'd been a robot, I could have done continuous motion and let this friction angle be phi sub k. And if phi sub s is greater than theta, the screw is what we call self-locking. It will remain in place under load W even after you stop applying P, because there's so much friction in the system that the handle won't rotate the other way, which is analogous to saying there's so much friction here between the block and the incline that the block would just stick and not translate down that incline. To lower the load, we apply Q in the opposite direction in figure 8.9b, which is no different than turning our jack screw handle in the opposite direction. And if phi sub s is less than theta, the screw will unwind under load W, and watch out for that. That's not the kind of jack screw you want to use with your car. You'll be out there changing a flat tire and all of a sudden the jack comes down, and look out below, as in for your toes. You apply force Q in the opposite direction to maintain equilibrium in the case where phi sub s is less than theta, which is no different with your jack screw than having a hold on to the handle and keep it from rotating the other way if you really had minimal friction in the screw threads. The lead L is normally the distance through which the screw advances in one turn, and the pitch P is the distance measured between two consecutive threads. And they're equal in the case of single-threaded screws, which are the most common. But if you have what are called double-threaded screws, the lead L is actually twice the pitch, and for triple-threaded screws, the lead L is 3 times the pitch. And in those types of screws, you're able to apply enormous amounts of torque as you rotate the screw and lift up your load. Here is sample problem 8.6 for how to calculate a clamping force in a clamp that's used to hold two pieces of wood together. It's called a C-clamp, and you probably use this in woodshop class, perhaps in middle school, perhaps in high school. The clamp has a double square thread with a mean diameter of 10 millimeters and a pitch of 2 millimeters. The coefficient of friction between threads is phi sub s equals 0.3, and a maximum couple M of 40 Newton meters tightens the clamp. Your job is to determine the force exerted on the pieces of wood and the couple required to loosen the clamp. And to solve this problem, we will represent the screw thread by an inclined block, and we'll determine the incline of the screw from the geometry which we're given. We'll find the force applied to the block by setting the moment of that force equal to our applied couple, which is 40 Newton meters. In step 1, we're going to analyze the screw threads in order to calculate the force exerted by the clamp. The screw is double threaded, so the lead L equals twice the pitch, which equals 4 millimeters. The lead angle theta and the friction angle phi are then found from the fact that tangent theta is equal to L over 2 pi r, and that angle then is 7.3 degrees, and tan phi sub s is equal to 0.3, and phi sub s equals 16.7 degrees. We now calculate the force Q exerted by the clamp. They told us that the diameter is 10 millimeters, so the radius is 5 millimeters. Then Q times R is M, which is the applied couple. So Q is 40 Newton meters divided by 5 millimeters, which is 8 kilonewtons. Our maximum applied couple, M, was 40 Newton meters, which is why that appeared in the denominator for the equation for Q. And our mean radius is just the mean diameter divided by 2. In step 3, we draw our free body diagram and then our force triangle for tightening the block, which is figure 1. And we can solve the force triangle to find force W exerted on the pieces of wood. Vector R makes an angle with the vertical, which is where our weight is, of angle theta 7.3 degrees plus phi 16.7 degrees, so that R is at an angle of 24 degrees to W. Q, of course, is a horizontal force, so we get a right triangle for our force triangle, with which we can calculate that W is just Q over the tangent of 24 degrees, and W is 17.97 kilonewtons. Step 4, we draw the free body diagram and force triangle for loosening the block. This time we subtract our 16.7 degree friction angle from our 7.3 degree incline, and we get a minus 9.4 degrees for the angle, so that vector R now is to the left of W in our force triangle. And Q, knowing W now, is calculated at 2.975 kilonewtons, such that the couple then becomes 14.87 Newton meters. And if you compare those numbers, you see that they're well under half the values that you needed to tighten the clamp, which is what I was saying before. When you use a jack screw, is that the one thing you notice when you're doing your engineering thinking as you sweat out there in the sun changing a flat tire is it takes a lot more effort to lift the jack up and get your car up in the air than it does to turn the screw the other way and let the car back down. Which is nice that at least after you're tired and frustrated and you finally got your spare tire changed out, that at least you don't have to put as much effort in order to finish the job and get the car back on the ground.